In continue of our discussion from the last lecture on different flip-flops, we discussed the new types of flip-flops. During the last lecture, we learned about latches and also a D flip-flop. Today, I will introduce a new flip-flop called JK flip-flop. Okay, first, let's see how is the circuit of a JK flip-flop. JK flip-flop is built from a D flip-flop, which it's like built from two latches. Okay, so D flip-flop is built from latch, and the JK flip-flop is built from D flip-flop. Here, let's assume we have a D flip-flop with inputs D, input clock, and outputs Q and Q bar. If you remember, I mentioned that this small triangle means that this device is a flip-flop, not a latch. Input D is connected to an OR gate. The OR gate inputs are connected to two AND gates, and output Q bar is connected to first input of the first AND gate, and output Q is connected to the second input of the second AND gate. The other inputs of these AND gates are connected to J and K. And this one is a JK flip-flop. How we show JK flip-flop? The symbol for JK flip-flop is two inputs J and K, J and K, one clock input, and of course two outputs Q and Q bar. Now we want to find the next state of the output. Of course, we know that for the D flip-flop, the next state of output is equal to D as we discussed. And what is D? If we look to D, we see that D is like output of a combinational circuit. So what is the combinational circuit output? It is a J Q bar, which of course is Q bar of T, plus K bar Q of T. Okay, K bar Q of T is here, and J, I'm trying to erase, okay, and J Q bar is here. Okay, so now that we have the characteristic equation of JK flip-flop, so this one is called characteristic equation of JK flip-flop. Okay, so we need to implement the characteristic table. We can simply implement the characteristic table from this characteristic equation like what we did for combinational circuits. The inputs of this characteristic table, of course, is J and K, and the output is Q of T plus 1. Okay, so if we have four different combinations for J and K, 0, 0, 0, 1, 1 0 and 1 1. Let's see, what if j and k both are 0? If j and k both are 0, this term will be equal to 0 because j is 0. What about this term? Because k is equal to 0, k bar is equal to 1, 1 times q of t, which is equal of q of t. So if j and q are equal to 0, q of t plus 1 is equal to q of t. What do we call it? We call it no change. So there is no change. Okay, let's continue. Let's continue next stage. What about, I don't know why my eraser like doesn't work properly. Okay, so what about if j is 0 and k is 1? If you look to this equation, if j is 0, this term is 0, k is 1, this term is also 0, so the output is equal to 0, which we call it reset. What if j is 1 and k is 0? Okay, can you tell me what would be the output? Of course, if j is 1 and k is 0, we will have, give me, okay, I don't know what's going on with my pen eraser. Okay, so if j is 1, this term will be equal to q bar of t. If k bar is 0, k is 0, k bar is 1, so this term will be q of t. So q bar of t plus q of t. What is, we know that any like a variable or with its complement is equal to 1. So the output will be 1. So we call it set. And finally, what if both of them are 0? If both of them are 0, of course, the first term of this equation is 0, and the second term is, sorry, if both are 1, sorry. If both are 1, the first term of the equation will be q bar of t, and the second term is 0, so the output is definitely q bar of t. So we call it complement. So if we look to this characteristic table, we can see that so far JK flip-flop is the best flip-flop. Why? Because it is not only able to set reset, it's also is able to create no change and complement status at the output. Okay, so JK flip-flop is the best, not the best, the most completed flip-flop so far. So characteristic table. Okay, so this one is JK flip-flop. Now that we know D flip-flop and JK flip-flop, it's time to learn about the next type of flip-flop, which is called T flip-flop. T flip-flop or toggle flip-flop. Okay, so how we build a toggle flip-flop or T flip-flop? We can create a T flip-flop using a JK flip-flop or D flip-flop. The symbol for T flip-flop is like input T, input clock, and output Q and Q bar. So this one is a T flip-flop. So how we can build this or construct this D flip-flop using D flip-flop? We can connect the input of a D flip-flop. So let's say this one is D flip-flop, input clock, input D, outputs Q and output Q bar. So we can simply connect the input D to XOR gate. XOR gate. One of the inputs of the XOR gate is connected to input D, and the other input of XOR gate comes from Q. So this one is how we construct T flip-flop by D flip-flop. And if we want to create a T flip-flop using JK flip-flop, what we can do, we can simply use a JK flip-flop clock input, J and K inputs, and of course we have output, and it's very simple. Using a JK flip-flop, we can simply connect both inputs together, and it's a T flip-flop. So if we try to find the characteristic equation of this flip-flop, characteristic equation, we can see that Q of T plus 1 is equal to D, which is equal to T XOR Q, or T Q of T bar plus T bar Q of T. So this one is the characteristic equation, characteristic table. We have one input T and one output Q of T plus 1. If T is 0, the output is Q of T. If we look to this equation, we can definitely see that if T is 1, the Q T of T plus 1 is QT bar. If we want to define T flip-flop in a sentence, I can say that D flip-flop is a flip-flop that complement the output as long as the input is 1. So as long as the input is 1 in each clock cycle, the output will be flipped. Okay, but when the input is 0, the output has no change. So we use T flip-flop to complementing the output. The best flip-flop to build counters is T flip-flop. Okay, so let's see one example for T flip-flop. Let's say we have this clock signal. It's a timing diagram. We have this clock signal. We need to mark the rising edges. So let's assume this T flip-flop is rising edge sensitive. Here is T input. Let's assume T input is like this, and the initial conditions of output is 0. So at the rising edge, we check the the input is 1, the output should be complemented. So the output changes to 1. In the next rising edge, input is 0, so output is no change until the next rising edge. In the next rising edge, input is 1, the output is 0 until the next rising edge. In the next rising edge, input is 1, output should be complemented, so it's complemented to 1. So this one is the way we can draw a characteristic table of T flip-flop. Okay, so the next thing I want to talk about it's a D flip-flop, or not just D flip-flop, any flip-flop. But here we talk about D flip-flop, but for all flip-flops this is true. So D flip-flop clear, with clear and preset. Okay, what is clear and preset? Sometimes we know that flip-flops have a memory. So in order to determine the output, not only the input is important, the previous conditions also is important. Sometimes we need to set the outputs in a in a particular state. Okay, set all of them to 1 or all of them to 0. Why we need to do that? For example, it's a counter. Counter is counting from 0 to 1, 2, 3, 4, 5, 6, let's say 7. We'll stop the counter. So the next time we want to use the counter, we have to reset the counter to 0. Okay, so next time we cannot start from 7 and count up. So when we use the counter and count it like from 0 to a specific number, the next time we want to reset it to 0. Or sometimes we need to reset it to 1. So for those counters that counts from um, uh, reverse countings from higher numbers to lower numbers. So we should be able to set the state of flip-flop to a specific value, to 0 or 1. So it's the reason we use preset and clear input. Okay, so in some devices such as counter, it is important to force the counter into a known initial state. Or initial state in counter is called count. Okay, so obviously it must be possible to clear the count to 0, which means all flip flops must have q equal to 0. Okay, of course it is also useful to preset each flip-flop to q equal to 1. Okay, now that we reached to this point, we want to apply this inputs to a D flip-flop. This can be done by using D flip-flop, which, as I said, it's not only D flip-flop. Any flip-flop can have like a preset and clear input. D flip-flop, which, not which, with clear and preset. But okay, so like we have it here, for example, we have a D flip-flop has input D, it has input clock, output Q, output Q bar. In addition of those, we have two other inputs. Do you remember what does these small circles means? They means that they are low active. So we can use input preset N and clear N. So this N mean like stands for negative due to these like circles. So how does it work? Placing a zero on the clear input will force the flip-flops into the state Q0. Will force the flip-flop to Q0. While clear N is equal to 1 has no effect. So clear N has effect when it is equal to 0. Clear N when it's equal to 1 has no effect. Similarly, preset N, when we put it equal to 0, it forces the flip-flop to a state Q1, while preset N equal to 1 has no effect. Let me write it down for you. So we say preset N, if it's equal to 0, Q will be equal to uh, preset, it's Q is equal to 1, not 0. When preset N is 1, no effect. Clear N, when it's 0, it sets the Q to 0, and when it's 1, it has no effect. Okay, so this one is how does this preset and clear input work. Okay, so and in the next lecture I will talk about a timing diagram for JK flip-flop and continue the lecture.